Hi, this is TheoryStation. I'm John Duggan. This program is Rational Choice Modeling. The series we're in is the Basic Formal Theory Toolkit, and this is installment 13 in the series. I've been talking about the multidimensional policy choice model, and now I want to shift gears and think about more of an economics mode, but to take some of the lessons from the previous installments and apply those. So I'm going to talk about I'm going to call it a public good provision problem. But it's actually going to be an extension of the cost-benefit analysis that we did before. The difference is that, if you remember, early on, we talked about a decision maker that has to choose the scale of some project and wanted to maximize net benefit, so benefit minus costs. Now what we're going to do is have two decision makers choose the scale of something, but now we're going to think about this as an amount of effort or resources contributed toward provision of some publicly consumed item. So, you can think about this as two people working together on a project, and the final quality of the project depends on how much effort each person puts in, or it could be contributions to some collective effort, whether it's provision of parks or national parks. It could be contributing to clear skies by not polluting. So we are going to think about this kind of problem where we have two decision makers, each choosing, let's call it an activity level. So so the decision makers I'll just label 1 and 2. And I'll use x1, which will be a non-negative activity level, be the activity level of decision maker 1. And obviously x2 is the activity level of decision maker 2. Now, the preferences of these decision makers are going to be in the form of a cost-benefit problem. So they're each going to derive some benefit from these activity levels and some cost. In general, they could evaluate these things differently. So in general, person 1, decision maker 1, could have some benefit function like this. In contrast to the original example, there's just one benefit function and one argument, that is one scale that goes in there. Here we have, I'm indicating a benefit function with a subscript of 1 so that we know it's decision maker 1's benefit function, and now there's two activity levels that enter in here because person 1's benefit from this collective effort will depend not only on their own activity level but the activity or contributions of the other decision maker. All right, so and then we could also have a general cost function here. I'll let that depend on decision maker 1's identity. Okay, but we're just going to have a decision maker. They're going to incur some cost of their activity level, but that only depends on their own level. Okay, so if it's a cost of effort, I bear the cost of my own effort, but if you are exerting some effort, you're absorbing that cost. So we could do the same thing for decision maker 2. That would be the general form of the problem. Here we'll look at a simplified model where the benefit function will be the same. It'll have the same functional form for each decision maker. So I'm going to drop the subscript, and it only depends on the sum of the two activity levels. In fact, I'm going to generalize that in just a little bit. We'll assume the cost function also has the same functional form, so I'll drop the subscript there as well. So, so let's say decision maker one's cost benefit problem would be to maximize this expression here. But let's put in a parameter to make this a little bit more general. So rather than have decision maker one's benefit depend equally on the two contributions, let's suppose that, well, let's allow person one's benefit to depend more on their own contribution than the other guys. Okay, so the way I'll do that is I'm going to write, again, this common benefit function now will just have one argument. Instead of the sum of the activity levels, I'm going to write x1 plus beta x2, where here beta is a non-negative. Actually, let's make it a parameter between 0 and 1. All right, so this parameter is going to control how much person 1 cares about person 2's contribution. If beta is equal to 0, person 1 doesn't care at all. This term here disappears, and person 1 just solves the usual cost-benefit problem. If beta equals 1, then person 1 cares about person 2's contribution equally. So this would be decision maker 1's cost-benefit problem, or to maximize this. And person 2's cost-benefit problem is going to be to maximize. Now they're going to choose an x2 instead of an x1. And they're going to maximize the same thing, but now from person 2's perspective. So things are going to be flipped here. Person 2 cares about their own contribution plus beta times person 1's, and then they absorb their own cost. So again, beta is the same parameter for each decision maker. It's between 0 and 1, and this is decision maker, oops, two's problem. And here I see I didn't say decision maker, but fine. So I want to make something clear here, because this probably is starting to look a little bit weird, because I have two maximization problems. So the way we're going to think about this is these two decision makers are going to be choosing their activity levels simultaneously. So person 1 is going to solve their maximization problem, but they're just going to make this choice at the same time as person 2. So they can't see what person 2 does and react. They just have to choose whatever they think is optimal. Person 2 is the same. Okay. So neither decision maker can react to the other, and so that means that to figure out what the optimal choice is, each decision maker has to formulate some expectation about what the other one is going to do, and so that leads us to the idea. Well, it leads us to game theory. And the idea of an equilibrium. So let me just write this out here. So decision makers choose their activity levels simultaneously, and that means that this situation we're talking about is technically a static game. Static because they both choose simultaneously and it's done. Nothing happens over time in this model. Game because, I mean, it might not really be fun, but it's a game in the sense that each decision maker is in a strategic situation where they have to anticipate what the other person is doing. And that leads us to the idea of a Nash equilibrium. Okay, so a Nash equilibrium is going to be a pair. It's going to be an activity level for each decision maker, such that, let me put bars on these. So a Nash equilibrium is where each decision maker is optimizing given correct expectations about what the other person is doing. So that means I'm going to write this in terms of two conditions. One is that decision maker 1 is choosing x1. Let me write it this way. Optimally, given the choice that decision maker 2 is choosing. So this activity level, this equilibrium level, solves the following maximization problem. Okay, this is the problem where person 1 is choosing an activity level to maximize their benefit as a function of x1. And now, right, so we're choosing x1 to maximize this thing. So it's the endogenous variable. But we're going to take person 2's activity level as fixed. It's a parameter of person 1's problem, right? They can't decide for person 2. They just have to have this expectation and do the best they can given that. Okay, so they're going to solve, they're going to maximize their benefit minus the cost, which only depends on their own activity level. And person 2 is doing the same thing. So x2 bar solves person 2's maximization problem. And again, now the objective function is going to be written from their point of view. So they're choosing x2 with person 1's activity level fixed at this sort of expected level, and then they bear the cost of their activity level. So the idea of a Nash equilibrium is that we're looking at an outcome, which in this case is a pair of activity levels, such that each decision maker is solving an optimization problem, which is a little unusual at first. You know, in calculus, you learn about solving a maximization problem, but here we have two. And it can be a little hard to wrap your head around at first. So why don't we, let's think about, well, let's solve this. And in doing this, for this discussion, I'm going to assume that there is a Nash equilibrium, and I'm not going to worry about the case where either decision maker is just choosing 0, okay? So let's let x1 bar, x2 bar be a Nash equilibrium such that both of these activity levels are strictly positive. Okay, so since person 1 is solving their maximization problem, well, we know that their activity level is optimal, so it has to, it's going to maximize their problem, so the first order condition has to hold. And if we differentiate the objective function of person 1, which is this over here, this is just a reminder. So the first order condition for this problem is going to be what? Well, we take the derivative with respect to x1, which is the endogenous variable, and we set that derivative equal to 0. So the derivative of this so I have the derivative here of the objective function on the left-hand side. That equals 0 in equilibrium, so I'm going to keep the bars on person 1's choices. And of course, I can put the derivative of cost on the other side by just adding that to both sides. And I get the first order condition for decision maker 1. The same thing holds true for decision maker 2. And that's the first order condition for decision maker 2. Okay, so what we've done is we have essentially converted this joint maximization problem, this dual maximization problem, into a system of 2 equations in 2 unknowns. If we can solve this, then we know, well, that tells us something about any Nash equilibrium where the activity levels are positive. Okay, so I want to just, let's make a couple assumptions about this, and I won't go on too much longer, and we can continue this in the next installment. Let's assume, just to get a handle on this problem, that this benefit function has this kind of concave shape. Okay, that's the benefit function for each decision maker, and that means that the derivative, for example, if you look at x and y, you'll notice that the function gets flatter as we look at higher activity levels. That means the derivative is decreasing, and we call that decreasing marginal benefit. Okay. Let's also assume that the cost function has this kind of convex shape. So we have increasing marginal cost. Those are really standard assumptions. You can imagine situations where they might not hold completely, but they're fairly intuitive. We've talked about them before, and we'll assume those here. Now, with those assumptions, I want to argue that in any Nash equilibrium, the 2 activity levels of the decision makers actually have to be the same. And that's not too surprising, given that the decision makers have the same functional form for their benefit and cost functions. It shouldn't be that surprising that they would end up doing the same thing. And we call that kind of equilibrium a symmetric equilibrium. Now I am getting into the weeds a little bit here, but partly it's because, you know, we've seen a lot of models now, and, you know, I think it's good to start not just seeing them, but start playing with them. So how would we go about showing that that these two activity levels are the same? First, let me just copy this. So what I want to do is, it's kind of a proof by contradiction. You can think about it as just elimination, process of elimination, but basically there's three possibilities, right? I'll write it like a tree, but we can have it might be that the two activity levels are the same, which is what I want to claim, or they're different, which means, well, either person 1's is less than person 2's, or person 2's activity level is less than person 1's. Because of the symmetry of the situation, I'm just going to argue that person 1's activity level cannot be less than person 2's. Symmetric argument applies that person 2's can't be less than person 1's, which leaves the situation that I'm claiming. And then I'll wrap this up. So I'm going to suppose that person 1's activity level is less than person 2's, and I'm going to show that that leads to a contradiction. And that means that, you know, the situation is not sustainable. It can't occur. So, all right, if that's true, remember that marginal cost is increasing. So if it is true that person 1's activity level is less than person 2's, then the marginal cost that person 1 is facing in equilibrium has to be less than the marginal cost that person 2 is facing. Okay? But we have these first order conditions. Okay? So we know that we know that person 1's marginal benefit is, well, it's equal to the marginal cost. So I'm just rewriting what I have up above. We know person 2's marginal cost is equal to their marginal benefit. Okay, but we've just deduced that person 1's marginal cost is less. That means that their marginal benefit is less. Okay? But remember, marginal benefit is decreasing. So if we draw it up here, here's this marginal benefit function. It's decreasing. So if person 1's marginal benefit is less than person 2's, it must be that this expression, x1 bar plus beta x2 bar, is greater than the expression x2 bar plus beta x1 bar. Okay, so that gives us okay. But then if we just subtract beta x1 bar from each side and subtract beta x2 bar from each side, then we have this inequality here at the bottom. But that doesn't look very much like a 1. But the key is if beta is less than 1, then we can divide through by 1 minus beta. But look, then we have we suppose that 1's activity level is less than 2's, but we deduced that it's greater than 2's. That's a contradiction. So what we've shown is that this branch can't hold by a symmetric argument. This branch can't either, which leaves this one branch. So in equilibrium, the activity levels have to be the same. That is, all equilibria with positive activity levels have to be symmetric. All right, so in the next installment, we'll continue this analysis and just draw more implications from this observation. I'll see you in the next one.